how's it going? Welcome back to the channel. In my last video I covered the brief history of computing, but in today's video we're going to cover the next chapter in the textbook after that, which is chapter 6, Computer Systems. So today I'll be running through the whole chapter, start to finish. There's a bit more in here than the previous chapter, the history of computing. So this will be a slightly longer video, I think, but we'll see how we go. So to start, what is a computer system? Well, a system is connecting parts interacting to achieve a common goal, just generally. So in a computer system, you have interaction between the computer hardware itself, the software on the computer, the data that is being processed, and the user. And a computer system can consist of multiple computers and programs. You can take, for example, if you're watching this on a laptop, or if you have a laptop, you have the physical components of the computer, which is the hardware. Then you have your software, like your browser. You have data and input, like the video or the website, and you have the user, which is you. So all of that is interacting and coming together to create a computer system. If you connect that laptop to the internet, this computer system expands like substantially, because you have suddenly connected yourself to just about every other computer out there. So we'll go on to computer architecture. In a computer, the architecture is how the components are laid out and connected together, both physically and logically. This is quite similar to house architecture, where an architect will design the layout of a house. They'll determine how many stories it has. They'll determine where the kitchen is, where the bathroom is. So this is quite similar to a computer, where the different components are laid out and interconnected in a specific way. For example, the von Neumann architecture, this was conceptualized by a computer scientist, John von Neumann, in the year 1945. It's widely used by many computing devices today, and it has 4 key characteristics. So there's a CPU, or central processing unit, to execute instructions. There's a memory unit that stores the data that is to be processed, and the instructions for processing the data, along with the results of that processing. Then there's a bus between the CPU and the memory unit, connecting the two. And then there's input devices and output devices to allow data to be inputted and results to be outputted. So we'll go over the components of the von Neumann architecture in depth. We'll start with the CPU, the central processing unit. It has 3 key components to it. So there's the control unit, which controls the operations of the CPU. You have the ALU, which is the arithmetic and logical unit, which carries out the arithmetic operations and the logical operations on data, as the name would suggest, using the instructions that are stored in its memory. Then you have the registers, which are a sort of easily and quickly accessible memory in the CPU. So there's a few types of registers here. There's the program counter, which keeps track of where the CPU is in the program, which allows it to keep track of what instruction is to be executed next. There's the data registers, which will store the data that is to be processed by the CPU shortly. And then the address registers, which will store the memory addresses for the data that is to be processed, or the results of processing. Then we have the memory unit. So there's 2 types of memory found in a computer. You have RAM, which is random access memory, and ROM, which is read-only memory. So they are quite different to each other. So we have RAM is short-term. The data is lost when power is lost, which is what we call it's volatile memory in that regard. But it is much faster. It's very, very fast. ROM, on the other hand, is more long-term storage. It's non-volatile, so it retains the data even after power is lost. But it is the drawback of being much slower than your RAM. So you would have your primary storage, like your RAM, which would store the data for the immediate use by the CPU. This is much faster. The Fetch-Decode-Execute Cycle. This is an important concept because it describes how the CPU carries out its operations. So how it works is the CPU will fetch the next instruction from memory. The instruction is found in a memory address and it's then stored in binary code. Then the CPU decodes the binary into an instruction that it can understand, and it then executes that instruction, and the cycle continues. It loops indefinitely. So those are the three components of the fetch, decode, and execute cycle. It's a fairly easy one to remember because the keywords describe the processes involved. The CPU clock then, it creates electrical pulses at a particular frequency to synchronize the running of all the components in the computer. And this makes sure that everything runs in sync and with perfect timing, because with the amount of processes going on per second, it can the clock makes sure that everything keeps in time and runs in sync with each other. Obviously, it's not a physical clock as I have pictured there, but that's just for illustration. The CPU speed, so this is typically measured in your clock speed. So a single electrical pulse can be equated to one loop of the fetch, decode, execute cycle. So the higher the frequency of these pulses, the faster the CPU can operate, because you have more fetch, decode, execute cycles running in a single second. CPUs can and typically do now have multiple CPU cores, which allow instructions to be executed simultaneously. So you can process things simultaneously, which will carry out operations and calculations and tasks much quicker. And then most modern CPUs now will have a CPU cache, which will store the items temporarily that are being written to or read from the memory unit. The bus then that connects the CPU and memory, I've used the bus here for illustration because it is similar to an actual bus. It transports the data between the memory unit and the CPU. But a bus isn't exclusive to this. It can be used all over the computer, and it is used all over the computer as a means of connecting units and transporting data. But this is what it does. It is a bus for the data, if you would like to think of it as that. Then you have your input and output devices, as we mentioned before. You have your secondary storage devices, such as a hard drive, your USB keyboards, or just any regular keyboard. You can have a monitor or a touch screen, because a touch screen can serve as both an input device and an output device, and a mouse as well is also an input device. More on the secondary storage. So as we talked about the non-volatile memory earlier, it stores the data indefinitely. So even when the power is lost, the data remains there, it remains stored, it remains intact. The data can be accessed at any time by the CPU. It doesn't have to be immediately. If it's stored in primary storage, the data is to be used immediately. The drawback of secondary storage is that it's slower, but it is, on the plus side, cheaper and bigger than your primary storage. So it does have a specific use purpose in the whole system. Like your hard drive or your SSD, your files are stored there and then loaded into your RAM to then be processed. The motherboard then, this is where everything begins to come together as a single unit, a single system. It's a circuit board that all the components in the computer are physically connected to. That includes all the components that I mentioned earlier. All the components are interconnected with wires that are built into the physical board itself. The material of the board is a non-conductive material, like a non-conductive fibers. And the board has ports on it that allow you to connect more components and devices. Like it would have a USB port to connect a USB flash drive or a USB keyboard and stuff like that. So the electronics of a computer then, we've gone over the components, the physical components, but how do the electronics work? So I mentioned in the last video binary. So binary signals can have two possible states. You can either be on or off, and we represent these with ones and zeros respectively. So if there is a signal present, an electrical signal present, we use 1, and if there is not a signal present, we use 0. This is used by all modern computers to represent information and data. This contrasts with the old analog systems, like an analog television, say for example, where a wide range of fluctuating values are used, and they can be subject to interference, for example. So different components of the computer control this flow of electrons through the computer, which is how it functions. So we're kind of getting into physics here a little bit. So these are the concepts of electricity and how it works. So electrical current is the rate at which electrons flow from one point to another. The voltage is the difference in the charge between an electron's current location and another. Resistance is how much a material resists or opposes the flow of an electrical current. An electron will move when the resistance is low and when the voltage is applied to it. So a negatively charged electron will try to move towards a positive charge, and that flow of electrons is manipulated by the computer to make it work. So how exactly does the computer manipulate these electrons? So there's a few components that it uses. A transistor, which I mentioned in the last video, it's a switch of sorts that can allow or disallow electricity to flow through it. We talked about in the last video how it was preceded, how you had vacuum tubes that came before it, and obviously these are much smaller, but they limit the flow of electricity. They can either allow it to pass or not allow it to pass. You have resistors, which reduce the electrical current flowing through it, which typically it'll convert some of the electricity to heat energy and allow the rest of it to continue through the circuit. And then we have a capacitor, which will store a small electrical charge for a short period of time. You might, if you've ever turned off a TV and noticed that the light stays on for a few seconds after you turn it off, and the light will slowly fade out. That's a capacitor releasing its charge. Then we have logic gates. So this is a very important concept. These are the arrangement of transistors to allow Boolean operations to be performed on the data. From our programming in Python, we will have used Boolean operators like and, or, or not, etc. So CPUs contain many logic gates, like millions, billions of these, and they're arranged in a specific way to carry out a wide variety of operations, like your mathematical calculations. So there's a few of them that we're going to go over. We're going to go over 5 different types of logic gates now. We'll start with the AND gate. So this is 2 inputs and 1 output. It'll only output 1 if both of the inputs are also 1, and it'll output 0 in every other case. So I've attached a table here. This table is called a truth table. It's used to represent the inputs and outputs of a logic gate. So you can see we have our 2 inputs A and B and our output of Y. So you can see if I input two zeros, I get a 0. If I input a 0 and a 1, I still get a 0. A 1 and a 0, I still get a 0. But it's not until I input 2 ones that I get an output of a 1. So A and B have to be 1 for our output to be 1. So that's where the name AND gate comes from. And then we have an OR gate, which also has 2 inputs and 1 output. But the difference here is that it'll output 1 if either input is also 1. So if we look at the truth table, again, you can see that even if only one of the inputs is 1, it'll still output 1. But if both inputs are 0, it'll output 0. Then we have a NOT gate. So this effectively just inverts the input. It only has 1 input and only has 1 output, but it'll just invert whatever input you give it. So if you give it a 0, it'll output a 1. If you input a 1, it'll output a 0. Then you have a NAND gate. So this is an AND gate followed immediately by a NOT gate. So what that means is that in essence it's an inversed AND gate. So you can see if we input 2 ones, this time we actually get a 0, but every other combination of inputs gives us a 1, and this is the inverse of a regular AND gate. Then similarly we have a NOR gate, which is an OR gate followed by a NOT gate. And similarly to the NAND gate, it's just the inverse output of an OR gate. So you can see that by inputting 2 zeros we get a 1, but in every other case we get a 0. So that's logic gates. You can look over them in the textbook on pages 136 and 137. They go into more detail on them, and there's also questions on them on 138 to do. But we're going to move on, and we're going to go over the general idea of interfacing and networking. So an operating system, you will have of course heard of operating systems, and you will have used them before. They're a collection of programs that control the operation of the computer and its programs and any of its connected accessories or devices or peripherals. So the operating system has a few important functions. It'll manage the sending and receiving of data from the I/O devices, or input-output devices. The user interface, as we call it, which, as it would suggest, is the interface that allows the user to interact with the computer. An operating system also handles the files and file systems. It manages the storage of programs and data in the computer's memory. It manages how the computer interacts with other computers. It controls the access and security aspects, and it also controls the hardware and how it interacts with the programs. So it has a lot of important tasks and functions there. So we have the concept of the layer model. So this is this shows where the operating system effectively falls in the whole computer system. So if we have a user using using an application on their laptop, let's say. So we start with the user. The user interacts with an application like Microsoft Word, for example. Then the application will then communicate with the operating system, which will help control how the application interacts with the computer hardware. So it bridges that gap between the application and the physical hardware of the computer, allowing the application to function. So the internet, of course everyone knows what the internet is, but people sort of don't have a proper definition. So it's a global network of billions of interconnected computers. All of them can communicate with each other. They're connected in a wide variety of ways, like your fiber optic cables, or like satellite, for example, like Elon Musk's Starlink technology. And we also have this idea of the Internet of Things nowadays, where everything is an internet-enabled computer, like your car, or like a doorbell, like a Ring doorbell, for example. Your TVs are now smart TVs. You have smart light bulbs that connect to the internet and can be controlled from your phone. So it's not just personal computers that are connected to the internet anymore. Every practical appliance or device in your home is now an internet-enabled device, which creates this wider Internet of Things. Then we have the World Wide Web. So this is, while it uses the internet, it's not the same as the internet. It was invented by a man named Tim Berners-Lee. You can see him there in 1989 while working at CERN. And he wanted a way of sharing this scientific knowledge and information between different scientists working around the world in different institutions and universities and such. So how it works is it uses the internet, and it transfers HTML documents, which we would now call websites, between different computers. And web pages, the World Wide Web, we can describe it as, like, different web pages all linked to each other. People, and again, as I was saying, people often think the World Wide Web and the internet are the same thing, or they use the two terms interchangeably, but they're not, and that's an important difference to point out. Then we have the client-server model. So this is, if you're accessing a web page, this is what will be going on in the background. So your computer, which is the client, will make a request to a server. This server is a type of computer that will provide a resource for a client computer like your own. So your computer, your client computer, makes the request to the server, and the server sends the information back to the client, for example, the web page that you're trying to access. And then your computer, say your browser, will render the web page that you've just accessed from the server. And the client-server model can have multiple servers and multiple clients all working together to carry out certain tasks or goals. Then we have communication protocols. So these refer to how data is transmitted across a network. And we can divide this up into 4 distinct layers. And each layer has a rule set. Each layer has a protocol which has a specific rule set to apply to to the data once it reaches that layer. So we have the application layer, the transport layer, the network layer, and the physical layer. And you can see I've given examples of protocols for each layer. So we'll go over these now. We have HTTP or HTTPS, which is a Hypertext Transport Protocol, or Hypertext Transport Protocol Secure. You will have heard of this one. You'll have seen it at the start of URL links. So this is a communication protocol where the client requests the resource from the server, and it allows the server to respond with the resource to the correct client computer that requested the resources. So you will, like I said, you will have seen it at the start of URLs used, to transfer web pages between a server and a client machine. Then we have so that operates on the application protocol layer. Then we go down to the you can see that there. Then we go down to the transport protocol layer. You have TCP, or Transmission Control Protocol, and how this works is this transports binary information or data in what we call packets. So these are small bundles of binary data, and it sends them out and makes sure that client computers receive these packets of information in the correct order that the server sent them out in. Okay. Then if we move down another layer to the network layer, we have IP, or Internet Protocol. So this creates the aforementioned data packets of binary information, and it routes these packets of information to the correct client computers via IP addresses. And we all would have heard of IP addresses. They're unique identifiers for a network or a computer. And so how this is working is it's sending the packets to your specific IP address because it understands that your IP address was the one that requested the information, the packets in the first place. Then we move down another layer to the physical layer then. So we have Wi-Fi. So these are radio waves. It connects devices wirelessly to the internet throughout your home, and it manages the flow of data around your Wi-Fi networks, like the network that you would have in your home, in your house. Then as well, we also have VoIP. So this is a voice over internet protocol. So this would be used for calling over the internet. It's a protocol for voice data or video call data, calling over the internet. If you've ever used Zoom or Microsoft Teams or WhatsApp or Skype or any of those internet calling services, this is the protocol used. Then internet hardware. There's a lot of definitions here in these few slides, but I suppose the best way to learn this is just to learn off these definitions, rattle them off on flashcards and such. So internet hardware, a gateway connects two networks that have different protocols. So two technologies, like different networks in the same organization. Then you have a router, which is what forwards the data packets that we mentioned between different computer networks, like the router in your home that'll forward the data between the internet, so the fire it out for a server, and the home computer, the computer that you're using. A network bridge then creates a single network from multiple network segments. A network switch forwards data only to the devices that need to receive the data, so it doesn't forward it on to all devices. And then a repeater can receive data and then retransmit it. So this is used when transmitting data over very long distances without repeaters in place. The signal may become too weak for the information to reach its destination. So repeaters are put in place to boost the signal strength as it moves along. Then cloud computing. So you will have used cloud computing before. It's the storing, processing, or accessing of data or services, programs over the internet by using custom designed servers for these tasks. So you will have used cloud computing before. You will have used the likes of Google Drive or Dropbox for cloud storage, but it's also got other applications. I've given NVIDIA GeForce Now as an example of video games over the cloud using an external server to run video games, and which are then streamed back to your computer. So there's a few benefits to cloud computing. You can buy as much or as little storage or computing power as you may need. It's quite flexible, which is sometimes called elasticity. Files can be shared between many different users, and you can have remote access to your files. So you can access your Google Drive and all the files on it, for example, from your computer at home, but you can also access those files, say on your phone when you're on the move, or if you sign in on another person's computer somewhere else, you can access your Google Drive and access your files. There's issues. There's always the risk of a security breach, which could potentially cause the loss of your files or the theft of data. And then there's the issue that for cloud computing to function, you always need a constant internet connection to sync up with the server. So if you don't have an internet connection, you can't, say, access your files on your Google Drive, which I'm sure is an issue that many of you have encountered in the past. So thank you very much for watching. That's a rundown of the computer systems chapter from start to finish. In the next video, I plan on talking about chapter 7, which is computational thinking, algorithms, and data representation, which consists of a whole load of things like abstraction and decomposition and the representation of data. So that's it's quite a long chapter, so it could take a while for that video to come out, but it will certainly be one I'll be working on. So again, thank you very much for watching, and good luck with the leaving.